Greetings, welcome again to this course on CFD. Today we will be doing fourth module for this week. Syllabus we have listed for this week: illustration on the performance of different interpolation scheme for convection term, and from this class we will move on to time advancement integration methods, arrangement of variables, pressure velocity coupling. There are different methods available: MAC, simple, different versions of simple, projection method. We will look into these details and then move on to next module. With regard to variables, once you define domain and mesh, then we need to select points where variables have to be computed. It is critical because it decides the way governing equations are solved, the programming easiness, memory requirement, and overall computational time requirement. There are three approaches in general: what is known as a staggered grid, collocated grid, and semi staggered grid. Let us look at one by one. The first one, collocated grid. It is all, you can also read it as co-located. As the name indicate, in this system all the variables are stored at the same location. Approximation for the derivatives are straightforward, programming is easier, memory requirement is minimum. If you look at the mesh arrangement, what is shown here is for the finite difference procedure, and what is shown on the right side is for the finite volume procedure. As you can see here, this is a location where all the variables are stored. So, in this example, the arrow going from left to right is for the u velocity, arrow going from bottom to top is for the v velocity, and the dotted point that is marked is actually indicating node or location where other variables are stored, scalar variables like temperature, pressure, or concentration. So, all the three variables, for example u velocity, v velocity, pressure, are stored at the same location. This is for finite difference arrangement, and if you are going for finite volume type of arrangement, then you can have definition at the center of the volume as shown here. So, this is a location where scalar variables are stored, and arrow going from left to right for u velocity, arrow going from bottom to top is for v velocity. As you can observe, in both the cases they are all defined at the same location. Let us say, for example, you are trying to find out first derivative dou u by dou x or the pressure dou p by dou x. Both dou u by dou x and dou p by dou x appear in the u momentum equation, and for both you need to find the derivative. And in this case, as you can see here, you are defining only grid, and the grid is same for both u as well as pressure. Hence, getting a derivative difference formula is easier. Same coding can be used just by changing the variable from velocity to pressure. You can obtain first derivative, say dou u by dou x and dou p by dou x, with much easier. Because you are using only same location, delta x is also calculated only once and it can be stored, hence it is easier and memory requirement is minimum. It is used when boundary conditions as well as its slopes are discontinuous. So, this co-located arrangement of variable is extremely helpful when the boundary condition as well as its slope is discontinuous. Like any other method, this also has some disadvantage, what is known as checkerboard problem. In the next slide, we will explain what is checkerboard problem. In this slide, what is shown in this figure is a computed pressure distribution on co-located arrangement. A particular control volume or the pressure cell is shown in the shaded portion. P is a node of interest. For example, west node and west face, similarly east face and east node are shown. Similarly, for the other side, that is north node, north face, south node and south face, they are also shown. Delta x and delta y is a element distance in x and y direction respectively. The numbers that is shown in this figure is 90, 40, 90, 40. This is the pressure field obtained, say by any procedure. Let us not worry about what is the procedure. If the pressure field happens to be as shown here, then how we will find out how the derivative of the pressure in x and y behave. So, obtain pressure at phase E and W by linear interpolation. The pressure gradient term dou P by dou x, for example, in the u momentum equation is shown as here. So, dou P by dou x equal to, so dou P by dou x for the cell that is shown is actually P at east phase minus P at W west phase by delta x, and that is what is shown here because it is dou P by dou x. Now, P at east phase is done by linear interpolation. Pressure at node P, point of interest, and pressure at node E, point the adjacent node, are used to get pressure at east phase. So, it is shown here P at capital E plus P at P by 2. Similarly, for P at west phase, you take pressure information from node interest P and west node, and linear interpolation is used, and delta x is there. Now, if you look at this overall, you have P P appearing in both the term with the minus sign in between. So, P P term gets cancelled. Finally, you have P at E minus P at W by 2 delta x. You can obtain similarly the other pressure gradient term dou P by dou y, which is appearing in second momentum equation or V momentum equation. Without going through the detail, you can immediately make a guess. Dou P by dou y is equal to P at n minus P at s by 2 delta y. Now, what is to be noted, you are interested to find out dou P by dou x and dou P by dou y, and you get expression without the node of interest term appearing. So, it is to be noted that pressure at the central node P does not appear in the final expression for this gradient dou P by dou x or dou P by dou y. Now, if you substitute the pressure gradient term in the discretized Navier-Stokes equation, then all the pressure gradient term will go to 0, which otherwise mean there is no source term appearing in the discretized Navier-Stokes equation, which is unphysical. So, that means the 0 source due to pressure in the discretized momentum equation, even though there is a pressure field appearing as shown in this figure, and this is quite unphysical, and this is a problem with collocated arrangement. Next arrangement is a staggered arrangement. As the name indicate, variables are stored at staggering location. Location or nodes where velocities and pressures are different, not only pressure, any scalar also are different. So, here is a figure to explain what is a staggered arrangement. For the same mesh, you can now observe at the center of the mesh is a pressure or any scalar variable is stored. Arrow mark going from left to right is indication for u velocity, and arrow mark going from bottom to top is for v velocity. So, u velocity variables are stored on the vertical line at this place, which is half cell distance from the center in the x direction. Similarly, v velocity cells are stored on the horizontal line as shown here, which is half cell distance in the y direction from the center of the cell as shown here. So, you have 3 locations, one for each velocity and one for pressure or scalar. whereas in the co-located arrangement you have the same location. Now, this results in different computation. Pressure nodes are the center, while the nodes for velocity are staggered in line with the direction of the component. There is one big advantage, there is a strong coupling between velocity and pressure. So, as we can interpret from this figure, the pressure at the center is responsible for the u velocity flow as well as for the v velocity flow as shown in the figure. Hence, there is a natural strong coupling between velocity and pressure, and this avoids oscillation in pressure as well as velocity field. Third arrangement is what is known as a semi or partially staggered arrangement. In this, velocity variables are stored at the same location, whereas the pressure or any other scalar quantity is stored at the staggered node or at the center. So, this is a figure that is explaining for the same mesh arrangement, u velocity and v velocity are stored at the one same location, whereas the pressure is at the center. So, it is in between collocated and staggered. It combines advantage of staggered as well as collocated, and it is found to be good for non-orthogonal grid. Still, it produces some oscillatory pressure or velocity fields. Now, let us look at all the three arrangements together. The left is a collocated arrangement, middle is a semi staggered or partial arrangement, and the right is a staggered arrangement. So, you can immediately get idea the advantage as well as disadvantage. So, in the case of staggered arrangement, because locations are different, you need to compute for each one of them separately, hence it involves some time and more memory requirement, whereas there is a natural pressure and velocity coupling in staggered grid arrangement. The next example, we are going to use only staggered grid arrangement, and that is widely used in many codes as well as commercial software. We go to the next important topic, what is known as a pressure velocity coupling. What is the background behind pressure velocity coupling, or what do we mean by pressure velocity coupling? By now, we know in general there are three governing equations respectively for three momentum or three velocity components, and there is one continuity equation. This is the minimum requirement for any fluid flow calculations. In each governing equation for momentum, there is a convection term, and we repeated many times before, convection terms are nonlinear in nature. In total, there are 4 variables, that is there are 3 velocity components and 1 pressure. So, number of equations equal to number of variables is satisfied. However, there is no separate equation for pressure, though it plays an important role in all the momentum equation. Velocity variables are, however, very strongly coupled, because you will observe, you know already also, that each velocity component appears in every other momentum equation, including the continuity equation. That way, velocity variables are very intimately coupled. Correct pressure field should be known, and that should be used in the momentum equation to obtain correct velocity field, which in turn satisfies both momentum as well as continuity equation. This process of linkage between momentum equation and continuity equation is what is known as a pressure velocity coupling. Now, this is very important stage in solving Navier-Stokes equation. There are many methods available. We are going to look at specifically 3-4 methods: Mach algorithm, simple algorithm, simpler algorithm, projection method. Let us look at Mach algorithm first. This is otherwise called marker and cell method. For any calculation, once you define mesh and you decide the variable location, you are able to describe boundary conditions. But what about all the internal nodes? All the internal nodes are initialized with some guess value. This step is called initialization. So, you start the solution with a guess value of pressure and velocity component. We will now explain the procedure for u momentum equation. The procedure is same for v as well as w momentum equation. Between time level 0 or between one iteration to the next iteration, velocity is intermediate velocity. Once you know the procedure for discretization, then you write down final discretized Navier-Stokes equation. In this case, we mentioned we will take x momentum equation, and that is what is shown here. So, the time derivative term is retained on the left side, all other terms are brought to the right side, which means all the terms are supposed to be known on the right side. U star is the intermediate velocity, and that is to be determined first, then it will be corrected. So, u star minus un by dt, that is a time integration. For this case, what is shown here is a first order Euler time integration. U with the superscript n refers to previous time level. All the terms on the right side, dou p by dou x and convection term, viscous diffusion term, we follow any procedure for discretization. Finally, we get this discretized equation. So, if you solve this equation, then you get u star. We name it a u star because it is intermediate velocity. The intermediate velocity may not satisfy continuity equation. So, if you rewrite this equation, take dt to the other side, un is also known, and that is also taken to the other side, and this is the equation for u star. So, if you solve, you get u star, and this is at one node location, and for 1D it will run from left to right, for 2D it will run the entire map. You can write a similar expression for v as well as w velocity component, but for y as well as z direction. As we mentioned just now, this u star, v star, w star are intermediate velocity component, and they will not satisfy or they may not satisfy continuity equation. So, if you substitute u star, v star, w star in continuity, then you get what is known as an error in the continuity, and it is referred here as d star. You write in the form of equation as shown here. So, dou u star by dou x plus dou v star by dou y plus dou w star by dou z equal to d star. D star is an error in the continuity, and this d star is used to obtain what is known as a correction in the pressure, and you prescribe a limit for d star if d star is greater than some prescribed value epsilon. So, for example, 10 power minus 3 or 10 power minus 5, that is a tolerance level you can accept. This limit is set by you for, and it will change from problem to problem. It can also be changed in one calculation itself between different time levels of the calculation. So, if the magnitude d star is greater than some prescribed value epsilon, then you set up pressure correction as shown. Delta p is a correction in pressure equal to minus beta d star, and what is beta? Beta is defined as shown here, omega by 2 delta t by 1 by del x squared plus 1 by delta y squared plus 1 by delta z squared. Now, omega in this case is what is known as a relaxation parameter. We will talk about relaxation parameter later. So, once you calculate beta, because all the quantities are known, then you can calculate delta p. Delta p is a change in pressure or correction in pressure. Velocity components and pressure are corrected as given here. What is shown here is again for only u velocity component. So, u star I comma j comma k, we are writing it for 3 dimension, hence we get 3 subscripts equal to u star I comma j comma k minus dt by delta x and delta p. The adjacent node also should be corrected, that is u star, you can see I plus 1 comma j comma k equal to the old one plus correction in pressure. Similarly, the pressure is also corrected. So, in this equation u star, that is on the left side, is a new velocity P star is a new pressure. You can use them as a U star or you can write it as U itself, it is immaterial. What is to be noted is this is a corrected velocity and corrected pressure. One can repeat this procedure for other two components V as well as W. Now, repeat this step for all the cells in computational domain until no cells has a magnitude greater than d star that you have specified. So, this procedure is what is known as a marker and cell method, and this is again a popular method. So, this class we have specifically seen arrangement of variables, 3 arrangement of variables, advantage and disadvantage associated with them. Then we understood the need for pressure velocity coupling. We explained one procedure, what is known as a marker and cell method. In the next class we will take another important method, what is known as a simple method. Thank you and see you all again next class.